So we're going to test in section 9.4, sigma 1 equals sigma 2. What does sigma 1 and sigma 2 represent?
Standard deviation of two separate populations.
Excellent. So this is going to be a test of two populations, standard deviations or variances. Standard deviation or variances. So equivalently, I could also test sigma 1 squared equals sigma 2 squared. And that's going to be kind of the same thing. So to do this, we're going to need a new distribution. So far we worked with three distributions. We worked with the z distribution, the t distribution, and then the chi-square distribution. Now remember, with the t distribution, we had something new compared to the z distribution. That was degrees of freedom. Same with this. Now we're going to need what's called the f distribution. And let me try and acquaint you a little bit with that. So like all of our distributions, the total area underneath this curve would be what? What's
1.
I'm sorry, one more time?
1.
Yeah, total area underneath the curve is 1. That's about where it stops all its similarities with like the t distribution and the z distribution. It starts at 0. It's not symmetric. And this is kind of wild. It changes with numerator degrees of freedom and denominator degrees of freedom. Changes with numerator degrees of freedom and denominator degrees of freedom. So there's two sets of degrees of freedom associated with our F distribution. And I believe I put the link in the chat, right? So if you wanted to play around with this curve, you can. Here's your F distribution. And I've got it kind of set somewhere in the middle. But you can change the degrees of freedom in the numerator and denominator, and just see kind of what you get. So, all right, nothing big. I mean, it tends to be the case that our F distribution is mostly going to be between, say, 0 and 3. It's only when your denominator degrees of freedom gets really small that it does have much more of a skewness to the right. But beyond that, it's just kind of a distribution. Nothing terribly exciting for us there. But the problem is for early mathematicians and statisticians is that getting these numbers wasn't as easy as it is for us modern statisticians. And to do that, to work with the F distribution, you'd have to have tables, lots of them. So there's 4 pages of tables. And because these tables were such a pain, what they did was they only decided to work with the right tail. So all of the area that they're calculating is for values of F that are in the right tail. You might notice that 0.025 is half of what we usually have. We usually have alpha is 0.05 in 2 tails. But if you half that, then you're putting 0.025 in the right tail and then 0.025 in the left tail. Now, I think Statistic can actually give you these values in the left tail, but the way we run our hypothesis test is that we're always going to be using the right tail for that kind of stuff. So that means instead of testing H naught such that sigma 1 squared equals sigma 2 squared, equivalently, what I can do is take that and kind of manipulate it. So this little bidirectional arrow means that this is equivalent. If I take H naught and divide both sides, say by sigma 2 squared, let's do that. Sigma 2 squared, sigma 2 squared. Then what? Well, then I'll get, let's do it in green here. H naught such that sigma 1 squared divided by sigma 2 squared equals 1. So that's how we're going to set up our hypothesis test in this section, is setting them up as the ratio equals 1. Keep in mind that that's equivalent to that. They're the same thing. Like I said, though, we're setting things up so that the larger of these variances is going to be in the numerator. That way it's equal to 1, or we're going to get something in the right tail. Now, there's a couple other possibilities for us here, depending on the exact form of the null hypothesis. You could have, for instance, let's see, let's do it here. H naught such that sigma 1 squared is greater than or equal to sigma 2 squared. And if I divided both sides by sigma 2 squared again, I get sigma 1 squared over sigma 2 squared is greater than or equal to 1. So you can still state your null alternative hypothesis like this, but we are going to be setting up our hypothesis test with the idea that the numerator of these ratios is going to be the bigger term. It's just a little nuance, a little pain that we got to deal with because of just what fun working with the F distribution used to be. Okay, so let's look at a couple examples about the F distribution and around the F distribution. Now, I think I gave you guys a handout on the hypothesis test for two population variances.
Yeah, you did.
So it should look like this. And a lot of this should be getting routine. State your null and alternative hypothesis, decide on the level of significance, input your data into Statistic, or at least your summary statistics. Find the p-value. Now your p-value is going to come from the tails of the F distribution. Your numerator degrees of freedom is associated with your chi-square sub 2. Denominator degrees of freedom is associated with, I said chi-squared, sigma squared sub 2, and sigma squared sub 1. The actual statistic itself that you use to get the p-value is kind of on the simpler side as far as our popular schema, as far as our test statistics are concerned. It's just a ratio of the variances. So let me circle it again this way. It's right here. That's all you have to compute. So that's something you can do actually by hand. I mean, it's not that bad. But we're going to use that to find the p-value. And then if the p-value is less than alpha, reject H naught. Otherwise, fail to reject, state your conclusion in words. There is something important up here at the top. Both of our populations, not just one, but both of our populations have to be normally distributed. Now, sometimes you can kind of wink and nod at this. If we were doing a t-test for means, then if you got a large enough sample size, then it tends not to matter. Larger sample size can cure a lot of ills with that test. Not true with the F test. With the F test, it's very sensitive to the idea that both of these have to be from a normally distributed population, both samples, I should say. So it is something to kind of watch out for. And some of the early questions on the homework are going to reflect that. So let's start out with this one. Which of the following is not a requirement for testing a claim about two population standard deviations or variances? So Well, the test requires that both populations have normal distributions. Now, that's certainly one of the requirements. The two samples are simple random samples. I don't think I put that on my sheet, but that's true. The populations are independent. So at this point, if you're doing an SAT test, if you've eliminated 3 of these, then the last one has to be your answer. And hopefully you're not going to spend too much time looking at that last one. But just for giggles, let's take a look at this last one. It says one of the populations is normally distributed. Well, what's wrong with this one?
We're testing a claim about 2.
Yeah, and both of them have to be normally distributed. So thank you, Laura. Okay, so just trying to help you out through a couple of homework problems. Let's continue with another one taken directly out of my math lab. It says if sigma 1 squared represents the larger of the 2 sample variances, can the F statistic ever be less than 1? Okay, so when we set up our hypothesis test and calculate our test statistic, we always set things up so that the larger variance goes in the numerator. So if the larger one's in the numerator, then the, let's see, so we got S1 in the numerator. So we can eliminate, for instance, this one right here because the larger one has to be in the numerator. Whoops. You know, I'm not sure I trust this conclusion here. Let's just, let's see. Can the F statistics ever be less than 1? Okay, well, we can eliminate another one. That's going to be this one. Because we have to put the larger term in the numerator, so that'd be our S1 squared. So we've at least eliminated 2 of these and we've given ourselves a 50-50 chance. Now, if a larger number is in the numerator than it is in the denominator, are you going to get a number less than 1 or greater than 1?
Less than 1.
The larger number is in the numerator. So give yourself an example. Give yourself a fraction.
Oh, I thought you said, never mind.
Okay. So do you want to guess again? If the larger number is in the numerator, is this ratio going to be less than 1 or greater than 1? You've got these 2 choices.
Greater than 1?
Greater than 1, yes. So there we go. So the answer is no. This ratio is always going to have to be greater than 1.
Okay. How do we know what, like, one is bigger than the other one? Like S2.
That is a little bit tricky. Now, as it turns out, with Statistic, you can kind of get away without making sure that you have to do, you know, the one is greater than the other one. But it used to be that we would have to take much more care. Now in Statistic, they can actually work with both sides of the F distribution. So like I said, it's not going to be as big of a deal. But what we used to do is we kind of would like peek at the data and make sure that the numerator degree of freedom, or numerator term was bigger than the denominator. So you'd set it up to be that way. All right, it's a good question. Thank you. Can the F statistic ever be a negative number? Now keep in mind, the F statistic is really based on this ratio right here. Something squared divided by something else squared. So
that would be no, because squares always, 2 negative squares would always equal a positive.
Oh, well done. Cool. I didn't even have to walk you through that one, but yeah. both of these have to be positive. All right, they can't be negative. So we can get rid of this one and this one right away. And let's see, because sample variances cannot be negative, the result of dividing squares, 298, yeah. So the correct answer is this one, it's C. Well done. Thank you. Okay, so one last thing in terms of kind of a homework warm-up problem. In testing the claim that sigma 1 squared is not equal to sigma 2 squared, that is, the variances are different, what do we know about the two samples if the test statistic is 1? Well, let me do that over here. Back up a little bit. So our test statistic is F. It's an F statistic, which is going to be the ratio of the variances. And we're told that that ratio is 1. So, okay. Let me clean this up. Let me rearrange it a little bit. What if I multiply both sides by, and this should be squared up here as well. What if I multiply both sides by the denominator? That's 2 squared on both sides. Can anyone tell me what's going to happen with this? I know this is algebra. You didn't sign up for algebra. My apologies. But what we'll get is S1 squared equals S2 squared. And that's kind of the conclusion that I wanted you to see. That if this is true, then this is true. What's that saying in words? Can anyone tell me what that says? This right here.
The two sample variations are equal?
Perfect. The sample variances are equal. And I'm particularly pleased, Shane, that you use the word sample, because that's what these are. These are samples. All right. Yeah, that's a sample standard deviation for the first sample standard deviation for the second sample, or I should say sample variances, because they're squared. If you didn't square them, then it'd be the standard deviations. So, excellent, excellent. Well done. All right, so there's kind of like a lot of preliminary stuff. Let's see about working with some actual hypothesis tests. Are we good with the preliminary stuff here?
What was the
Yes.
answer for the last one?
Oh, so let's take a look here at our choices. Looks like it'd be B. The two samples have the same standard deviation or variance. So, yeah, that was our conclusion. That's what Shane came up with. And it's right there as choice B. Let's take a look and see if we can eliminate the other one. The two samples have fairly different standard deviations or variances. No, that's not true. The two sample standard deviations come from populations with the same standard deviation or variance. Well, that could be what we're testing, but that's not what the F statistic equals 1 tells us. The F statistic equals 1 tells us that the variances and also the standard deviations have to be equal. This other choice here, C, that we're going to eliminate, the proper notation for that would be sigma 1 squared equals sigma 2 squared. That would be the population variances are the same, or you can also write the standard deviations are the same. But that's what C is saying there. It's talking about the population and not the sample. Remember, those two things are different. Okay, so does that help out with part C here, for example, B? Okay, let's turn our attention to one of the problems, and that'd be example C here. Researchers measured skulls from different time periods in an attempt to determine whether interbreeding of cultures occurred. Results are given below. Assume that both samples are independent, simple random samples from populations having normal distributions. Use a 5% significance level to test the claim that the variation of maximal skull breadths in 4000 BC is the same as the variation in 150 AD. So you're looking at two different skulls, two different groups of skulls, trying to determine, if certain characteristics have changed over time. Now, a lot of times what I like to do when I do these types of problems is not just use sigma 1 and sigma 2. I like to use notation that reflects the problem that I'm working with. Now, in yellow here, I've got the claim that we're testing. Test the claim that the variation of maximal skull breadths in 4000 BC is the same as the variation in 150 AD. So let's write that down. And I guess I shouldn't put H naught just yet. What I really should do is look at sigma for my 4,000-year-old skulls versus sigma for my 150 AD skulls. Now we're testing a claim that they're equal. Is that claim going to be part of our null or alternative hypothesis?
No.
Yeah, thank you. Has to be the null, because only the null hypothesis has the possibility of equality. What's that put in the alternative hypothesis?
Not equal.
Yeah, perfect, not equal to. Nice. It's not a bad time to also note that this is our orange claim, AKA the original claim. Why do I want to note this?
For the conclusion?
Yeah, for the conclusion. Yep. Now, if you look at the data, the one of these that has the bigger variation is actually the 150 AD. You could regard this as being equivalent to sigma sub 150 over sigma sub 4000 equals 1. I don't think we have to worry about that with our software stat disk, but and in some other softwares, or especially if you're doing it by hand, you might have to. I think we can get away with doing things more or less as usual. But what it does is this allows us to just use the right tail of the F distribution. All right, so that's kind of a very lengthy step 1. Someone make me look good. What's step 2?
Determine alpha.
Alpha, good. And alpha was given to us as 0.05. Step 3, want to put this in stat disk. And for stat disk, you're going to go to a predictable place. You're going to go to the analysis. And then from there, hypothesis testing. And then from there, should be kind of obvious if you're looking at the menu, standard deviation, 2 samples. Now, before I turn to StatDisk, I might want to take note of the data that I need here, which is really just going to be two things. I'm going to need to know what N1 and N2 are, and then sigma 1 and sigma 2. I shouldn't put, no, it's not sigma 1 and sigma 2. Ah, shame on me. Does anyone know what this should be?
Should it be S1 and S2?
Yes, thank you, Dakota. S1 and S2. Because you're dealing with sample standard deviations, not population standard deviations. Now, I think both sample sizes were 30. So N1 and N2 are 30. S1 is 5.11 and S2 is 5.39. With that, let's go over to StatDisk. Analysis, hypothesis testing, standard deviation 2 samples. Not that I'm not already there, but I just wanted to go through it just once for grins. All right. Now, as typical when we're working with hypothesis tests, the first thing we're going to do is adjust the alternative hypothesis. In this case, do we need to make any adjustments, or can I use the alternative
You're
as,
not making any adjustments.
yeah. What we're doing is the sigma 1 is not equal to sigma 2, so we're okay there with that first one. Significance level is fine as well. Sample size for the first population is 30. Sample standard deviation is 5.11. And then 30 again with a sample standard deviation of 5.39. Now, one of the things that they did give us in our our problem was that the data was normally distributed for both populations. And bam, there we go. So the F statistic is right here, 0.8980, et cetera. But that's not what I really need here. Just by the way, I do want to point out that you can actually get that F statistic for yourself if you take and plug those in. Now let's clear out some stuff here so that it doesn't look too intimidating. And clear this one out as well. If I just take parentheses 5.11 divided by 5.39 and square the whole thing, I should be able to get that exact F value. There you go, perfect. So the actual calculation itself is really simple. But what is that statistic telling us? Well, we usually don't base our conclusions off the F statistic. You could. In fact, StatDisk makes it pretty easy. If you fall between the red lines, that's the fail to reject region. If you fall outside of it, then that's the reject region. So the critical values are the points that separate the rejection region from the fail to reject region. And you can see that we're inside the critical values so that you'd fail to reject H naught. But that's not how we've been doing our hypothesis test. How have we been doing our hypothesis test? How would you make your conclusion based on this?
The p-value?
Yeah, your p-value. So step 4, our p-value is right here, 0.077584. Or it's not, I said it wrong, 0.77584. All right, 77. And that leads us to step 5. What are we going to conclude in step 5 based on the p-value?
P-value is greater than alpha.
Excellent. The p-value is greater than alpha. So someone else finish it up for me then. If the p-value is greater than alpha, what are we going to decide about H naught?
We failed to
Failed
reject.
to reply.
Yeah, failed to reject. Now let's put in fail to reject H naught, because sometimes people fail to reject HA, which is wrong. So fail to reject H naught. Yay, almost done here. What's left?
State the conclusion.
Yeah, state the conclusion in words. So for that, that's why we took note of our original claim here. That the original claim contains the possibility of equality. So let's take a look at that, along with the wording of our conclusion. And let's come on up a little bit. Let's get rid of these and work it afresh. Does the original claim contain the condition of equality? Yes. Do we reject H naught? No. So that starts us out at B. There's not sufficient evidence to warrant rejection of the claim that. So we'll start out our conclusion this way. I'm so happy the author gives you this. I mean, students have done much better in terms of stating their conclusions once the author started putting this as part of the handouts from this book. So there is not sufficient evidence to reject the claim that not sufficient evidence to reject the claim that. And for what follows next, you might want to go back to the original problem. So that's here in section 9.4. And I've got it in yellow. Just state in words the claim that you were testing. So there's not sufficient evidence to reject the claim that the variation of maximal skull breadths in 4000 BC is the same as the variation in 4000 or 150 AD. So there's not sufficient evidence to reject the claim that the variation of maximal skull breadths in 4000 BC is the same as the variation in 150 AD. Now I know it feels like it gets a little bit wordy here at the end. I guess the thing that I would always say is keep your instructor happy. I want to see that. I'm placing a premium on this conclusion because this is really what you got to do in statistics. You got to come up with some results that you can share with somebody. I mean, if you just told the average person, oh, the p-value is less than alpha, reject H naught, they're going to look at you blankly. So you need to be able to relate your conclusion in words, especially now that we got all kinds of software to help us out. This becomes a more important part of your work. Whew. All right. How's that one looking there?
Good.
Great.
Cool. Cool. All right. Let's try another one. And I think this next one is going to involve some data. So Well, let me see if I can't find that. I'm hoping that's question D here. Okay. So let me first start by grabbing the data, post it in the chat for you guys. And I hope that this goes through. I know that we've had problems with the chat a little bit and the data. So let me know if this works for you. And we should be able to put that into StatDisk. Once you grab the data from StatDisk, click on the StatDisk Online icon. That should take you back to the sample editor. And let's see, I've got some stuff there already. I'm just going to paste mine in columns 3 and 4. Now, occasionally people write me and say, oh, well, my data didn't work here. It was giving me some error that my columns were on unequal length and things like that, or found a character as expecting numerical data. Sometimes, now in this case, I pasted all of this stuff in blue. Sometimes you can paste in a hidden character. So you can look for these. You can click on the cell, and if there's a space there, you can delete it. Sometimes you might have to repaste the data after clearing all the data out. So hit the clear button here and then start again. So I'm just trying to give you a little heads up on, you know, a couple of things that can go wrong when you're trying to use technology.
Also, if you're selecting one of the values, like if you had 81 highlighted and then you tried to do the thing, it would also give you an error because it doesn't register it as being a thing. So you have to click off the data entirely.
Oh, okay. Good to know. So maybe if you're highlighting some of it, you can do an analysis on part of the data. Maybe that's what it's trying to do. But in any case, good to know. So make sure that you're not highlighting just like one cell or something like that. Thanks, Dakota. Let's go back here. So listed below are the interval time intervals between eruptions of a geyser. You know, I just don't know why they're afraid to say Old Faithful. I don't know. They denude all these problems of anything colorful at all. But if you ever get a chance to go to Yellowstone, it's really worth it. Old Faithful erupts for about, you know, 3 or 4 minutes every 90 or so minutes. And it's just beautiful. It shoots jets of hot steam and water out into the air about, I don't know, up around 150 feet. And this is just like a natural thing that just happens year round, 24/7. So kind of cool. The National Park Service tries to predict when the next eruption will be based on previous eruptions, how tall those previous eruptions were, and how long they lasted. We actually did a problem earlier this semester about those predictions, and they're not good. I mean, they're okay, but you know, it's just in general tough to predict. So, okay, I think you get the idea. Like I said, if you get a chance, go there. Oh, and let's see if that'll, yeah, and this one down here, that's Morning Glory Pool. If you see Old Faithful, take the 1.5 mile hike to see Morning Glory Pool. It's just stunningly beautiful. Those different rings are different colors of bacteria living at different temperatures. So, okay, let's get back to our problem then. Listed below are the time intervals between eruptions of a geyser. The recent times are within the past few years, and the past times are from 1995. Does it appear that the variation of times between the eruptions has changed? Use a 5% significance level. Assume that the two populations are normally distributed. Now, they're a little bit vague here in terms of what they want you to do. But we're looking to see if the variation, so that's telling you what parameter to use, of the times has changed. So, what would that be in terms of symbols if the variation has changed?
Would it be not equal to?
Let's say to me that they're not equal. This right here. But why can't A be our correct null hypothesis?
Because HO has to have an equals.
Perfect. You can't have something that doesn't have an equal sign as part of our null hypothesis. So in striking these out, at least you can get rid of this one and give yourself a much better chance of guessing correctly. So let's see here. Well, these other two have the wrong alternative hypothesis because they don't have the not equals to. So C is the correct form of this, equals and not equals. So that's our step one. So this is example D. Step one. H no. Now it doesn't matter to me. We can use sigma 1 squared and sigma 2 squared. We can use old and recent. We can use 1995 and 2015. Doesn't matter. All right. Don't hear anything, so we'll just use sigma 1 and sigma 2. Where sigma 1 is our older ones, sigma 2 is the newer ones. HA should be a 1. Should be not equal to. Somebody help me out with step 2. What's step 2 going to be?
Identify alpha.
Identify alpha. Awesome. Alpha was 5%. Now step 3 is put in the data. So let's at least gather some summary statistics from here. What we need is N1 and S1, and then N2 and S2. I need both of those. So looking back at the problem, oh wait, they're not there. Why aren't they there?
Because we have the data.
Yeah, use the data. And using the data is going to afford us another opportunity. Let me remind you that when you do these types of hypothesis tests, there we go. There was an essential assumption that you had to meet, and that is that both populations have to be normally distributed. So if they're not normally distributed, you really shouldn't be using this test. Well, because we actually have the data, we can do this test. So let's take a look. Let's see, Statistic. We've got our data. So we'll go to analysis, hypothesis testing, standard deviation, 2 samples. And our alternative hypothesis is good. Oh, we need to change something though. What is it that we need to change? Use data. So we're going to be using data, not summary statistics. We're not going to plug in the mean and standard deviation, sample size, that kind of stuff. We're just going to let Statistic figure it out from the data. Now the form of our alternative hypothesis is still correct, so we're looking good there. Significance 0.05. And let's see. For me, the data is going to be in columns 3 and 4. Now, technically, I really should be doing something first. Actually, you know what? I am going to take time to do it first. You can keep going with this if you'd like. But I really should do this. Underneath data, is normality assessment. I should look at my data and make sure that it's from a normal distribution. If I look at the first column, what do you think? Does that look like it's from a normal distribution?
Yes.
Yeah.
Yeah, it's not too bad. All right, I'm a little bit worried about this one out here, but when I look at the normal quantile plot, it looks pretty good. And in particular, when I look at the Ryan Joyner test up here, you fail to reject normality at the 5% and 1% significance level, meaning the data wasn't bad enough to prove it wasn't normal. So we're okay with that one. Let's take a look at the other population. Or is it good enough just to look at the first one?
No, you need both.
Yeah, thank you. You got to look at both. And the second one doesn't look too good. In fact, it's bad enough that you can reject normality at the 1% and 5% levels. So realistically, you probably shouldn't be using this test. Now, that said, let's pretend that the data actually did satisfy the normality assumptions for both populations. But in reality, we shouldn't be proceeding with this test. All right, we'll select go too soon. Hypothesis testing, come on. There we go. So use data, 5% significance level, columns 3 and 4, and bam. So if you need your test statistic, that's just the ratio of the variances, that's here. What value am I looking for from here? What am I trying to find?
P-value?
Awesome. The p-value for us is 0.22285. Yay. So that brings us to step 5. What are we going to do on step 5? What's our decision going to be?
Fail to reject.
Ah, well done. Thank you. Fail to reject. To reject H naught. Our p-value is greater than alpha. So if the p-value is high, H naught will fly. So we're going to fail to reject. Now, one thing that I forgot to do was circle my original claim, but I think in going back, this was our original claim because we were testing to see if there was a change in the standard deviation, in the variation. So let's use that along with the wording of our hypothesis conclusion to finish up step 6. Let me delete a couple of these. Come on. There and there. Okay, so does the original claim contain the condition of equality?
No.
Nope. Do you reject the original claim?
No.
No again. So it brings us down to D. Somehow I feel like we don't use D that often, but here it is. There's not sufficient sample evidence to support the claim that the variation between the times of eruption has changed. Hey, so not too bad. And where am I getting that last part? I'm just getting it from the original problem itself. So let me jump down here to D. The variation of the times between eruptions has changed. That's the claim we're testing, so that's going to be part of our conclusion.
Wait, Professor Parent,
Yeah.
wouldn't it's not B, like there's an equal sign in the original claim.
So the original claim to me, is really this one right here. Sigma 1 squared is not equal to sigma 2 squared. That's what I see as the original claim, because we're looking to see, has it changed? Meaning, are they different? So to me, that's the original claim. And that wouldn't have the possibility of equality. Do you see a difference, Shane?
Yeah, yeah, that makes sense. Thank you.
Okay. All right. I mean, it's okay to see it different. But I was just going to ask you for why then. But if you're in agreement, that's good. There is not sufficient evidence. I missed a word. Sample evidence to support the claim that the variation between the times of eruption has changed. All right, not bad. Yes.
I have a question about the step 6. So why did we say that it's D from the hypothesis test wording, not B?
Because in my mind, the original claim is this one. That's the claim that we're testing. And that doesn't include the possibility of equality. So that puts you down the bottom branch on our hypothesis testing. Let me go back to that right here. But I mean, Shane was kind of thinking this along the same lines as you did. So let me look back at it with us. No, unless you disagree, I think the original claim is the alternative hypothesis. And that puts us down here for our first decision. And then certainly we didn't reject, so that puts us even further down for our second decision, which is D.
All right, awesome, thank you.
You're welcome. Anything else on this one? Okay, well done, well done. All right, that's it for section 9.4 and chapter 9 for that matter. So we'll stop things here unless there's some further questions. Cool, well, good luck.